Assalamu alaikum. Welcome back to this amazing stream, a continuation of what we were speaking about 2 weeks ago, testing universal common ancestry with Dr. Paul Nelson. Welcome, Dr. Paul, back to the stream, and it's wonderful to see you again.
Thank you so much for having me back.
Brilliant. So just as a quick sort of recap, guys, we did part 1 already. You can go onto the channel and have a look about 2 weeks ago. This is the second part, and we're going to be doing the third part next week. So over to you, Paul.
Okay, today I want to focus on molecular data, which I will be considering in more detail as Subor indicated next week. But this will introduce us to some of the main issues. So very briefly, the motivating question on the table is, can the theory of universal common descent be tested? Last time I dealt with points 1 through 3, and today I'm going to add points 4 and 5. But I'll begin with a short recap of point 3 just to set the frame for what we'll be talking about today. So in this part, I want to focus on the prediction from universal common descent of the universality of the genetic code, which from the mid-1960s, roughly until the late 1980s, was a standard prediction in textbooks and in the primary literature. But what happened when that prediction failed? Why did universal common descent emerge unharmed? So that will be the motivating question in particular for today's discussion. So brief recap, the main points from part 1. Universal common descent cannot be an axiom or first principle of biology. The theory must be testable against data. However, the perfect generality of universal common descent, which I discussed last time, and I refer you to the recording of that presentation for more details, requires helper or auxiliary theories in order to make testable predictions. So schematically, we cannot go directly from universal common descent to the observables. We need to link that theory or couple it with some other part of our biological knowledge in order to generate testable predictions. So in the case of the prediction of a universal code, the auxiliary theory in question was that of functional invariance. In other words, that the code, because of its centrality to molecular biology, really to all the functions of the cell, could not vary. And then that gives you a prediction that you can check, namely the genetic code should be universal no matter what organism or species one examines. So just to help make this easier to grasp, let's assign some arbitrary numerical values. Of course, real biological predictions don't do this, but this is just going to help illustrate what I'm talking about. So as I said, the perfect generality of universal common descent requires auxiliary theories in order to make testable predictions. So let's say that without those theories, we have a prediction of 0 or the prediction is indeterminate or unknown. So let's couple that, let's couple universal common descent now to the auxiliary theory of the functional invariance of the code. So there's our theoretical coupling right here. And then let's say, just give it an arbitrary value of 7, just some numerical value to illustrate the point. Now notice where all the predictive strength is coming from. If we put our schema together here, you'll see that universal common descent by itself doesn't yield anything that we can test or that we can observe in a test. Functional invariance, however, does give us a value here. So in this schema, universal common descent is doing no work except to supply a geometry.
Sorry, Dr. Paul. Are you sharing the presentation on the screen?
I have been the whole time.
Okay, because it didn't actually appear on the screen.
Well, I hit share screen. I'm not accustomed to the StreamYard.
Yeah, no
I'm
problem.
very
Because
sorry
I thought you
about
were,
that.
no worries. I thought you were doing an introduction before you shared the screen. No worries.
All right. Well,
There we go. There we go. It's here now.
I'll just skip up to where I was. I'm very sorry about that.
No worries at all. I just thought you were doing a general introduction. Could you just go back a few slides, if that's all right, and just summarize again? Because I think I was
Sure.
trying to. Yeah. There you go. Perfect.
All right.
Thank you.
I apologize.
No worries. No worries.
StreamYard is not. I normally use Zoom, so my apologies. This is what we'll be focusing on today. I addressed these points last time, and I want to focus on predictions made by universal common descent when it's coupled to other theories. In particular, I want to focus on the prediction of a universal genetic code. When that prediction failed, why did universal common descent emerge unharmed? So, as I said, the main points from part one: universal common descent cannot be an axiom. It must be testable against data. However, because of the way it's formulated, what I call the perfect generality of universal common descent, it requires auxiliary theories in order to make predictions. So in the case of the prediction of a universal genetic code, the auxiliary theory concerns the necessary functional invariance of the code, which then allows us to predict universality, which we can then check by observation. So this gets us back now to the slide where I was. If we just put in some arbitrary numerical values just to illustrate the point, universal common descent by itself predicts nothing, or the prediction is unknown or indeterminate. So let's couple it to the theory of functional invariance, and that gives us a value. Again, this is just an arbitrary number to illustrate the point. Now notice where all the predictive strength is coming from. In this case, it derives from the theory of functional invariance, because without that, we don't know what we're predicting, which means that universal common descent is actually doing no work here for us except to supply a geometry. So we will say more about that geometry in just a moment. All the content flows from the theory of functional invariance. Okay, when I realized this a few years ago, namely that the empirical content was due to the auxiliary theory, not to universal common descent, I wanted to kick myself, right? It was so obvious. I thought, why didn't I grasp this before? But then it occurred to me that other biologists and philosophers probably realized the same thing, namely that universal common descent by itself is untestable. And sure enough, that was the case. So this is a selection from a much larger literature of biologists who have grasped this problem. So in 2007, Lars Vogt, who is now at Hanover University in Germany, but at the time was at Harvard, published a paper in the journal Cladistics where he said universal common descent by itself cannot rule out any imaginable character distribution. What that means is if you look at different species and observe their characters, universal common descent doesn't forbid any particular distribution of characters. As he puts it, a given tree hypothesis, evolutionary tree hypothesis, is logically congruent with any specific observable evidence of character state distribution. A given tree, in combination with descent with modification as background knowledge, does not prohibit any specific character state distribution pattern. As he goes on, there's no deductive link between any tree hypothesis and any specific character state distribution. One cannot think of any observation which, in case it would represent a true statement, would allow one to conclude the falsity of a clade or a given cladogram through modus tollens. Okay. And that same point was made the next year by Oliver Riepel at the Field Museum here in Chicago. And it's something that he has stressed actually throughout his writings on this question. Common descent hypotheses cannot rule out any possible character distribution. So as he puts it, all tetrapods have lungs. That proposition is a statement in the form of a universal law. However, we know that lungless frogs and salamanders exist. There is no universal law of evolution that governs character distribution. Character distribution is historically contingent, and the evidence for that fact is character incongruence. Okay, so let's consider a hypothetical situation. Let's say we have a population of single-celled eukaryotes like yeast, and we're going to look at a protein coding open reading frame, a gene that codes for gene XYZ, a hypothetical gene. So here's our population, and the cells all have gene XYZ. That's this little cartoon. The gene is represented here out of proportion to the rest of the chromosome, just so you can visualize it. And let's suppose that our governing theory is evolution by descent with modification from the last universal common ancestor, or universal common descent. What should we expect to observe about gene XYZ as we look in other populations of yeast, or as we look in other species of yeast, or as we watch this particular species as it goes forward in time? Okay, I'm going to give you now all possible evolutionary outcomes for that particular gene. So we have an ancestral state and a descendant state. Here are the cells. It's possible that there will be no change at all, that the sequence will be completely conserved from one generation to the next. Maybe it's under such stringent selective surveillance or control that the gene cannot vary. Its protein product is essential, so no variation. Or we could have partial change. In other words, there are some mutations in the open reading frame that modify the sequence, but detectable similarity remains to the progenitor state, and we would still assign homology between these two open reading frames. Or mutations could completely saturate the sequence, leaving no detectable similarity, so that the open reading frame is entirely modified by mutation. Or the sequence is lost. It's eliminated entirely from the cell, or it is replaced by horizontal transfer from another sequence coming in, an exogenous open reading frame coming in from some other species. All of these are possible outcomes. Now that creates a problem for us, right? What then does universal common descent assert? Well, it says there must exist a geometry of material descent from an unknown common ancestor here, where all these possible outcomes here on the right could have occurred. Now, the problem is, for the empirical content of universal common descent, any theory that is consistent with whatever we observe is not actually telling us anything about the world. So if I have some theory that tells you that whatever you see will be consistent with my theory may be true, but you have no way of determining that, right? Because it's consistent with whatever you observe. That's problematic. We want our theories to run the risk of being wrong, making predictions that may turn out not to be the case. That's the only way that we can test. All right. So how can we generate predictions from universal common descent which would not be consistent with any possible observation? Well, there's a legendary German proverb, peasant proverb: if the rooster stands on the dung heap, it will rain tomorrow, or it will not rain tomorrow. Consistent with whatever we observe tomorrow and actually telling us nothing, because all empirical possibilities have been covered. So to avoid this, to avoid having an empirically empty theory, we need to borrow a rule from elsewhere. And that's going to come from our independent auxiliary theory. So to generate testable predictions from universal common descent, which again, because it's perfectly general, needs help to do so, that rule will need to forbid certain potentially observable outcomes. We have to rule them out. Okay. Now, this is beautifully illustrated by the textbook prediction, which, as I said a moment ago, was in the literature from roughly the mid-60s when the code was solved until the late 1980s or early 1990s. I've certainly learned it as an undergraduate studying evolutionary biology from 1980 to 1984 at the University of Pittsburgh. This borrowed rule comes from genetics, molecular, and cell biology. Namely, the code, the genetic code, is so important to all functions, all organismal functions, that once established, it cannot vary. And we've already given this a name. Let's call it for short functional invariance, or FI. So we have a genetic code present in LUCA, which will have a DNA genome, and therefore will need, and proteins, and will need a code. And here is our rule, functional invariance, and we couple it to this geometry of universal common descent, which enables us to make a prediction. All right. So we put the rule there, and we get a very clear and strong prediction of universality of the code. No matter what species we examine, we should see the same code. So this prediction, you can find, if you find a biology textbook from, let's say, 1985 or from the late 70s, flip to the section that discusses how we know that universal common descent is true, and you'll see this prediction there. Whoops, sorry. Can you still see my slides, Sabur?
Yeah, I can.
Okay, because last time I accidentally turned them off. I just wanted to make sure. So this was...
No, I'm keeping an eye out.
I'm sorry?
I'm keeping an eye out to make sure that doesn't happen now.
Oh, wonderful. So this was actually predicted in the early 60s in Science, in the journal Science, prior to the elucidation of the code. It was already clear before the code was solved that if there was a code and common descent was true, universal common descent was true, that the code would be universal. So in their paper in 1963, Hinegardner and Engelberg predicted that the code would be universal because it could not vary once it got up and running. As they put it, the genetic code, once established, would therefore remain invariant. A very clear prediction, and I encourage you to look up this paper. It's not terribly long, just a few pages, and it's beautifully reasoned. So this became, as I said, the most widely cited evidence for universal common descent. So we can, on the basis of what we observe in the major domains of life, infer that the common ancestor, LUCA, would have had a DNA genome, a genetic code, enabling information transfer from the realm of nucleic acid to the realm of proteins via RNA. And here it is. This is the RNA expression of the code. This is an RNA codon table. So we're going from the DNA library to the realm of proteins, the main cellular actors, via this translation table. And of course, there are many beautiful and interesting features to the code that we won't have time to discuss today, but you can see that if you want proteins, and if you want those proteins to be specified by nucleic acid, you're going to be moving from one kind of chemistry to another. And of course, the business end of the code will be transfer RNA, and this will be the translation table mediating information transfer. Obviously central to all cells that we know. And because it was thought that the code could not vary, namely that mutations would be inevitably lethal, the expectation was that wherever we look in the tree of life, we should find the same code. Again, a beautiful, strong prediction coming from universal common descent when it is coupled with this theory of functional invariance. So we can express it this way. Here's a typical, you can note the date here, 1985. This is a typical textbook expression of the prediction. The code would be retained because any change in it would be disastrous. Thus, we expect the genetic code to be universal if all species have descended from a single ancestor. Okay, place your bets. From 1963 until today, September 18, 2021, how did our prediction fare? Well, not very well. In fact, there are so many variant codes that if you are working with a group that has a variant code, like ciliated protozoa, Tetrahymena, for instance, illustrated here on this cladogram, you need to go to the NCBI, which I'll show in a moment, the NCBI page where the variant codes are listed, so that you won't make a mistake if you are reading from DNA sequence data and trying to predict protein structure. If you read through the so-called universal or canonical code, you will generate incorrect protein amino acid sequences. You need to use the specific code for your group. So this is from a review paper in 2015 saying the genetic code, we thought it was immutable. We were wrong. So here is this page at NCBI that's regularly updated because new codes are being found all the time. So you have a whole variety of codes here, some mitochondrial, others in the nuclear code. And as I said, this grows all the time. It's updated sort of semi-annually. It's due for another update, by the way. I went and looked at it, and there are new codes that have not been incorporated. All right, what happened to our prediction? This one. Okay. And now, please, audience, you've got to think very critically, put on your philosopher hat, because we're going to try to dissect or disentangle what's going on with this prediction. You got a makeover. It was finessed. Okay. So Matthew Cobb is an evolutionary biologist at Manchester, and in, I think it was 2015, he wrote a book on the code, very beautiful book about the discovery of the code. I actually have it here sitting next to my computer. And he points out the non-universality of the code was completely unexpected and went against all the assumptions of all the researchers who had been studying the code. These discoveries showed that, strictly speaking, Jacques Monod was wrong. What is true for E. coli is not necessarily true for an elephant in all respects. Okay, observation tells us this is not true. Now we have a logical problem. Nature, she is standing there and she's written a ticket. She's got a fine in her hand. Some part of our theoretical bundle here has to pay for the failed prediction. Actually, earlier today, as I was thinking about this talk, I did a truth table for this. And the one thing that cannot happen in a case like this is that this is true and this is true, right? It's an element, it's a principle of logic that you cannot have two true premises that generate a false conclusion. It's a principle of material implication. So somebody over here has got to pay because this isn't the case. And nature is standing there somewhat impatiently with her arms crossed. Someone's got to pay the fine. Okay. Cobb says, well, you know, universal common descent won't be paying anything today. Thank you very much. And he passes the ticket down the table to the auxiliary theory. And this is how he puts it. Although the genetic code is not strictly universal, this has not altered our view of the fundamental processes of evolution at all. There is no dispute that life as we know it evolved only once and that we all descend from a population of cells So 3.5 billion years ago, known as Luca. So what's happening here logically? Well, functional invariance goes out the window, and universal common descent is protected from observational challenge. All right, you can do that. UCD is not going to pay any fines. All right. Look what happens now to the empirical content of universal common descent. Watch what happens to its predictive strength. So our new auxiliary theory is the code may vary. So let's put that in here. The code may vary. Now we have no idea what we're going to see when we look at a species. Maybe it will have the canonical code. Maybe it won't. There is no predictive strength anymore. It's out the window. It's gone. Because this is indeterminate. And as a consequence, universal common descent is telling us nothing about what we will observe. We may see variant codes. We may not. We just have to wait and see. That's a theory that has been bled white of its predictive power. Since the auxiliary theory, Fi has been dumped, the testable content of universal common descent, as far as the genetic code is concerned, is now indeterminate. And it's again consistent with whatever we observe, which means universal common descent is not actually telling us anything about the world. Okay, this is not a good state for a theory to be in. It is not healthy for a theory to be consistent with all possible observation because it's not doing any work for you. And what we want theories to do is to tell us things about the world that might not be the case, because it's only in that respect that we can check the accuracy of the theory and improve it if necessary. A theory that's consistent with all possible observation is not a healthy theory. All right, I'm going to finish on time, and that's a wonderful thing. In the genomic era, which is roughly from the mid-90s until today, so we're looking at, I would say, a 25-year interval, a quarter century now, an increasing number of evolutionary biologists and geneticists are unwilling to do what Cobb did and let universal common descent off the hook every time an observational fine must be paid. So I'll give you just a few examples, and then we'll conclude and we'll have some time for discussion. Eugene Koonin runs a very productive lab at the NCBI. And in 2007, in a major paper called The Biological Big Bang Model for the Major Transitions in Evolution, he said, the tree of life does not exist. So he bailed out of that single tree rooted in Luca. He jettisoned that geometry in the light of genomic data. And one of the main motivators for him to do that is a phenomenon that has a really horrible long name, non-orthologous gene displacement, often abbreviated NOGD. That's really fascinating when you begin to learn about it. So let's say in a microbial group, some microbial bacterial species, let's say, we have a particular metabolic pathway or pathway for some cellular function that requires genes A, B, and C producing proteins A, B, and C. So we say, well, this is the canonical pathway to enable this particular cellular function. But then we look in another bacterial group, maybe in the same clade, like the proteobacteria, and we see gene K, which is not homologous with gene A. It's producing protein K, which is not homologous with protein A. B is still there. So we observe homology at the second step in the pathway. But at the third step, we observe gene Q producing protein Q, which is not homologous with C, yet they are enabling the same cellular function. Now, there are many, many examples of this. It's a phenomenon that deserves to be much better known. But Koonin, who does very large-scale bioinformatic analyses of thousands and thousands of genes. So he really surveys broadly across microbial groups and eukaryotic groups. He is really dedicated his career to these kinds of broad-scale surveys of the distribution of genes and their protein products. In 1999, so this is just here about 5 years into the genomics era, he published a paper with two colleagues where they argue that DNA replication, that fundamental cellular process that present in all cells that we know, may have evolved twice independently because the hardware, the proteins involved in DNA replication in the bacterial domain when compared to archaea and eukarya are not homologous. Yet they're doing the same thing. They're replicating DNA. So he picks up a signal there, looking at DNA replication, and then surveys a broad range of other essential cellular functions. And in a paper in 2016, he said, the universal core of life has shrunk almost to the point of vanishing. There are very few functions in cells that are monomorphic. That means that they're using the same genes from one group to the next. And he concludes there is no universal genetic core of life remaining owing to the ubiquity of non-orthologous gene displacement. So if you think about that schematic that I showed you earlier of universal common descent plus some auxiliary theory generating predictions, in the light of failed predictions, Koonin is going back and he's saying, maybe it's universal common descent that's at fault. Maybe there was not a last universal common ancestor. In other words, there's a very different geometry at the root of the tree of life, which actually isn't a tree and may well be a forest of separate trees. So this paper is in press, all right? It's brand new. And by the way, I will provide the citations for this presentation to Sabor, and he can put them in the notes section on the YouTube version of this recording for anyone who wants to follow it up. Eric Baptiste is an evolutionary biologist at the Sorbonne, and in a paper with two colleagues, and I really should have their pictures here too, and I apologize for that. He's the senior author on this paper. This is still in press. It's brand new. They argue that there is so much non-homology, lack of homology among the gene families in microbial groups that we need to rethink how we do comparative genomics at a fundamental level. So in the paper, they say a glaring proportion of gene families is simply not shared between most cellular lineages. And they go on, it becomes a priority to explain the origin of genes without homologs outside a given lineage. This apparent lack of homologs encourages the deployment of models of gene origination that are more complicated than the divergence from a single last common ancestor. So LUCA is fading away in their understanding of biological reality. And again, if we go back to our schematic, in the face of an ocean of anomalous data, they're going back over here and they're saying, maybe this is the problem. And the predictions that we have been deriving from this theoretical coupling that turn out not to be the case, rather than sacrifice the auxiliary theories, what we really ought to do is rethink the whole bundle and rethink this in particular. And I would like to encourage the audience to dig into this, because the ocean of anomalous data is only going to grow with each new genome that's sequenced. And more biologists and philosophers of science, for that matter, are going to have to confront what they're going to do, the question of what they're going to do with this bundle. And this, frankly, is a question that is orthologous to the question of intelligent design. I'm an intelligent design theorist. a notorious one, in fact. But Koonin and Baptiste and other evolutionary biologists whose work I did not have time to mention don't support intelligent design, but they are keenly interested in coming up with a better geometry for the history of life than universal common descent, which they see as now failing in the face of a very large body of anomalous data that is growing really on a daily basis, because DNA sequencing has become so rapid and inexpensive, and the signal is not going to go away. So I have plenty of time now for discussion, and I thank you for your patient attention.
Thank you for that, Dr. Paul. That was a really insightful, as always, presentation. Before we get to the... Sorry?
I was wondering if I should stop sharing the screen so that you can see my face.
Yeah, so what I can do is, right now I've removed it and I can add it at any point. One of the things I wanted to actually ask you is, I've shared the slides again. Could you go back to the slide of, I believe it was near the beginning with some Oliver and Lars, when they were speaking about, yes, right here, perfect. So, yep, this exact slide. So it's very clear that at least the way that the vast majority of the biological community is thinking, that they don't really see any data that could actually go against universal common descent. So Koonin and others, would you say that they're outliers, that the majority still, for them, everybody has to pay the fine, but universal common descent just doesn't?
Actually, I would say that the shift in opinion on this question is happening remarkably rapidly. So I had to leave out a lot of material for lack of time. But if you go into the literature on the root of the tree, the branching of the three major domains, there's widespread agnosticism. And even when one comes to the, for instance, the last eukaryotic common ancestor, rather than say there was a population that was ancestral to all eukaryotes, many theorists now are saying the genetic diversity that we observe in eukarya is sufficiently great that we have to reconsider whether there was a last eukaryotic common ancestor. So what's happening, I don't know if you can see, can the audience see me?
Yeah, they can, yeah.
Okay, what's happening is there's a fracturing that's going on that's starting at the base of the tree and working its way up into the major domains and then farther up into the branches. And the biologists who say that universal common descent is good to go, they tend not to work in these areas. They're way off on some, in dealing with some clade, way off in the mammals or in the fishes. And as far as they're concerned, everything's fine. That's not the case, though, for those who actually try to infer the properties of Luca and relate this hypothetical entity Luca to the diversity that we see. So I guess I would disagree with you. I would say that for those who work on a day-to-day basis, like Koonin or Baptiste or Raoult in France, I mean, the list is long. Biologists who have to deal with these very large-scale questions have become increasingly agnostic about the truth of universal common descent. And I think that's going to accelerate. There was another aspect to the talk, again, that I had to omit, and that is that many biologists have an intuition about the origin of life that it was an extremely improbable event, and we're just lucky to be here. So they tend to marry that intuition about the origin of life with genetic data, and they say, look, I know the code is going to be very hard to evolve. I'm just glad to get it once. And by some improbable pathway, we got the code once, and now that's over. So any organism that has a code, no matter how different it may be, traces back to that singularity. This is actually not a strength of evolutionary theory. It's a major defect of evolutionary theory, that it relies on extremely improbable events to get things up and running at all. So there's a lot that goes into how one evaluates these universal common descent geometries. But if you had told me when I was a student that this would be happening today, that biologists would be rethinking this basic geometry, I just wouldn't have believed it.
Yeah. Thank you for that answer. And it's very good to hear that actually there is this change happening, and, you know, universal common descent is being questioned. So these guys are not outliers. Nonetheless, there's a few follow-up questions to this. One's more of a philosophy of science question in terms of the broader implications of this. But just before we get into that, because you raised the issue of the improbability of the origin of life, right? So this is something which I think is really important. I mean, you know, popularizers like Dawkins have also said that they just need that one stroke of luck, he calls it. Others have said we just need one miracle and we can explain the rest, right? So they all have all these types of things. So I mean, the first thing to note is, and I'm just putting this to you, isn't that a very materialistic assumption that because we cannot imagine something so complicated coming together, you know, in this way, it has to happen once? And then in a way, the theory itself is there to try and fuel materialism. So it becomes a you know, self-fulfilling prophecy or positive feedback loop. You know, could you sort of explain the assumptions that are being made here?
Yes. The Israeli philosopher of science, Iris Fry, in, I believe, 1995, had a wonderful paper, I think in the journal Biology and Philosophy. I'll provide the citation when I send you the bibliography for this talk. She said, actually, the view held by people like Dawkins and actually many neo-Darwinians, Ernst Mayr, Francis Crick in certain moods, Jacques Monod, that we're just lucky to be here, right? We got lucky in the cosmic lottery, but the antecedent probability of the origin of life via a natural chemical pathway is effectively zero. And we spin the roulette wheel, the cosmic roulette wheel, and everything fell into place once. We had that singularity of abiogenesis, and here we are. Fry, in her analysis, says this is effectively a creationist position. It's a wonderful paper, and she's a philosophical naturalist, so she's not making a case for creationism. What she's saying is, epistemologically, the structure of that inference is invoking what she calls a near miracle, and she said the problem with the view is it's then becomes effectively impossible to do any lab work or bench work on the origin of life, because an event whose antecedent probability is indistinguishable from zero, there's no point in running experiments because you're never going to be able to recreate this chemical pathway. And she argued that a near miracle view of the origin of life, such as was held by Dawkins and Mayr and others, really shuts down science on the question of abiogenesis. So Christian de Duve, whom I met a few years before his death, Belgian Nobel laureate in medicine and physiology, he argued that to do any research at all on the origin of life, you have to assume that the independent events in that pathway have probabilities as close to 1 as you can make them. Because if you're going to chain together a series of independent chemical events, you're going to have to take the product of those probabilities, and you want to push that towards 1. Right? So to do research on the origin of life, it behooves you to say it happened by a deterministic or quasi-deterministic pathway that we have to discover. So I actually think it is a glaring weakness in the evolutionary worldview that they invoke a lucky roulette wheel for the origin of the first living thing. It's basically a materialist, we call in the States a Hail Mary pass, right? You just throw the ball down the field and hope that someone catches it.
Yeah, absolutely. Another question is in regards to the broader implications of this false prediction. Because it is a very strong prediction that was made. And then the whole idea of, well, couldn't we see this from a purely Koonian point of view, that there is a prediction that's made from a theory, and that prediction is then falsified, and then there are ad hoc hypotheses made to prop up the theory. And the problem here is, how do we then say that it is testable in any meaningful way? Because if the auxiliary theory is malleable, you can always replace it with something else, and the universal common descent is not up for questioning, then the question goes back to where we started, which is, what is the actual point of making predictions if those predictions are not going to mean anything if they turn out to be false? So, normal science, revolutionary science, where are we? And it seems like, we are definitely at a point where the existing regime has some serious rebellion problems going on within its territories.
Oh, I very much like what you just said. I actually entered the philosophy of science as a 19-year-old by reading Koonin, and was able to see science in a way that I had never imagined. And I think that his reconstruction of what happens at these revolutionary periods provides a lot of insight. One of the things that happens when you chain together ad hoc hypotheses to save the phenomena, to borrow that phrase from actually medieval astronomers, what happens is you end up with theories that are such hopeless kludges that they, again, don't do any work for you. A theory that is chasing after every anomaly and finding a way to fit that anomaly via some ad hoc hypothesis to the core theory becomes a lumbering, useless monster. I think of the classical example of what was happening with Ptolemaic Aristotelian astronomy as it was in a state of decay, where epicycles were being added to epicycles and so forth, and they actually got very good at it in terms of fitting the data to these perfect circles that they were using, but the theory became increasingly unwieldy. And I think right now evolutionary biology, which is over 160 years old if we date it from 1859, has really become a lumbering monster. It's a terrifying thing to open an evolutionary biology journal and see the ad hoc hypotheses that are accumulating, again, almost on a daily basis. It makes the theory very unwieldy, and it's hard to know what it actually predicts. You don't want a theory that by being patched ends up being consistent with everything. That's not healthy.
Yep, at all. And one of the interesting things about this entire, debacle is the whole sort of arguments that they make against intelligent design proponents is, well, you don't have predictive power. Well, it's better not to have predictive power. I mean, if we were to accept their argument, than to have predictive power, which is so malleable, is absolutely meaningless.
Right. It's a misuse of the term predictive power in that context.
Yeah, absolutely. I mean, one of the things which I think is important to highlight here as well, and this really comes out in what Lars is saying here, is any given hypothesis is logically compatible with whatever evidence, whatever observation you're going to see. So sometimes, when we get individual questions from people confused about, the whole discussions between creationism and design and Darwinism, is, they'll go to, well, there's this particular behavior which Darwinists are saying fits with their theory, or there's endogenous retroviruses, or there's this, or there's that. This is the argument that we should make when it comes to any arguments which are being used by the Darwinists, which is, well, if that behavior, or if that particular sequence that you're saying is evidence of the theory was not there, and we had X or Y or Z, you would still be saying the same thing. So in a way, what is your argument? I mean, we cannot really, and this is why I think it's very important that philosophy plays a major role, because we cannot have an argument, a purely scientific argument, if there is this massive disadvantage where no possible observation can challenge the current theory.
You're right. And years ago, many years ago, in fact, in a journal, research journal that I was keeping at the time, I was concerned that I was insulating my own ideas about design from observational challenge, because I was at the same time a student of evolutionary theory, and I saw this pattern of protecting the core theory by either sacrificing the auxiliary theory or adding ad hoc hypotheses, to use Koonian terms. So I made a list of testable predictions or data that, if I saw these things, would make me seriously rethink my design position. Things like the spontaneous formation of long RNA chains under plausible prebiotic conditions, or in a Drosophila population that's undergoing mutagenesis, the origin of novel features that are that can be transmitted in a stable breeding population, right? Adding an extra pair of wings and have that extra pair of wings be functional and stable. In other words, I made a list of things which I thought, I don't expect to see this. And, that is a very healthy exercise to do under whatever circumstances or whatever science one is studying. Because, as Feynman said, the easiest person to fool is yourself. And, I love risky theories that are potentially in danger from observation. That's how we know we're actually saying something about the world.
Yeah, absolutely. And, I think just to be a bit fair, there is nuance to, if there's a prediction that's made that turns out to be false, it doesn't necessarily mean we throw it out. There are instances in which you can actually get rid of the auxiliary theory, and it's perfectly fine to do that. So, we're not sort of pushing this naive falsification, but despite that, the Darwinists were very clear, categorically clear about junk DNA, orphan genes, and the genetic code and other things, and they turned out to be consistently wrong. So just so that no one makes a straw man of your points, Doctor, we're not saying because of this, therefore we can throw it out. However, I do think there's an important point to keep in mind, which is when things are falsified, such as the universal genetic code, the auxiliary theories that are there to, let's say, which were initially hostage to to the evidence, when those fail, then the replacement auxiliary theories, they have to be in place to actually patch up the formula, you can't just have a placeholder of we're not sure, but we definitely know it's not universal genetic, universal common ancestry. Because what I find, and maybe I missed it during your presentation, I hope I didn't, but the replacement for the existing auxiliary theory is not something that is sufficient.
No, it isn't. It's actually, in my term, it's indeterminate. If you have I saw this actually in the case of theories about the causal structure of animal development. So now we're not dealing with the whole tree of life, we're dealing with just the metazoa. Again, it was a standard textbook prediction that early developmental stages in the animals, in the vertebrates, let's say, ought to be conserved because mutations to those stages are overwhelmingly destructive to the embryo. And you can find that prediction in textbooks. And then when early embryogenesis in a variety of animal groups was studied, it turned out to be very diverse. And in this case, again, the auxiliary theory paid the cost. And you're right, I don't want to advance naive falsificationism, but if there is a pattern of protecting the core theory of descent, where the auxiliary theories are always absorbing the blow, my question is, what is that core theory actually telling us?
Yeah.
And I realize that testing is complicated, and I take very seriously the Duhem-Quine thesis that it's not always clear where the problem is. But I would encourage the audience to, have their philosophical radar finely tuned to to detect these kinds of patterns in reasoning, and to give their auxiliary theories a chance. There's knowledge there. In fact, you could say we know a lot more about the auxiliary theories than we do about 3.5 billion years of evolution, which we were not able to observe directly. We have to infer.
Yep, absolutely. I think another point to highlight here is we can list a whole bunch of failed predictions from universal common descent. However, the Darwinists can sometimes come up with an argument which is, it sounds on first pass like it has some sort of weight, but when you look into what they actually are trying to do, you actually find out it is a way of hoodwinking people. So one of the things that you hear them say is, well, if this theory was wrong, then, we should be able to find rabbits in the Precambrian, or so, something like this. The problem here is that you can't come up with an absurd prediction, which we all know is absurd. I mean, because, an intelligent design proponent would never make a prediction that, I think Darwinism is wrong because I'm hoping to find rabbits in the Precambrian. So we're not making that argument on our end, but your arguments are being made from your theory. So there's an asymmetry here, which I think is important to highlight, because the rhetoric is quite strong when people hear these sorts of arguments.
You're right. And the reason the so-called Precambrian rabbit would be significant actually is interesting to unpack, and maybe we can do that in another session. Just to whet the appetite of the audience, Precambrian rabbits are found all the time. That is, the stratigraphic distribution of fossil groups is constantly being modified, often by tens or more millions of years. And the whole notion of ghost lineages is a way of repairing the damage from the failed prediction from I guess it's not really from stratigraphy, because stratigraphy is providing the anomalous data. The failed prediction from an evolutionary model of where fossils ought to be. But I'm looking at the clock, and it looks like an hour has elapsed.
Yep.
And again, I thank the audience. I apologize for my slides not being up at the beginning, but I will be providing all the citations and some additional materials to Subor for posting on the YouTube link. And I look forward to joining this group again.
Brilliant. I thought we were going to do part 3 next week. Is that right?
Well, I'm not sure I can,
Okay.
but I would like to schedule it, as soon as possible to sort of, strike while the iron is hot.
Yeah.
But we can talk about that later.
Sure. Okay, brilliant. So for anybody watching, the notes and all the references, they will be available. Thank you, Dr. Paul, for this insightful lecture, and I really do hope that the people watching are watching this with an open mind, that this is some very strong points against the current Darwinian regime. And I think we should, since we there's a lot of talk about regime falls, we should actually speak about it in these type of terms, because the rebuttals that we do get, they do sound as comical as some of the propaganda you get from falling regimes. So thank you, Dr. Paul, and hope to see you again.
Thank you.